IRAS, the original pioneer of the infrared cosmos. Launched in 1983, IRAS was the very first space telescope to map the entire sky in infrared light. Before IRAS, the infrared sky was largely unknown. Over its 10-month mission, it was a discovery machine, cataloging hundreds of thousands of infrared sources and discovering new comets, the dusty disks around stars where planets might be forming, and entire galaxies that shine brighter in the infrared than in visible light. IUE, the marathon runner of space astronomy. Launched in 1978, this joint US-UK ESA telescope was designed for a 3-year mission, but operated for over 18. It was the first space observatory to be operated in real time by astronomers from a ground station. IUE studied everything in the ultraviolet spectrum, from comets in our solar system to the halos of distant galaxies and supermassive black holes. COBE, the telescope that provided the first baby picture of the universe and won a Nobel Prize. Launched by NASA in 1989, COBE's mission was to map the cosmic microwave background, the faint afterglow of the Big Bang. It not only confirmed the Big Bang theory with stunning precision, but also made the monumental discovery of tiny primordial temperature fluctuations, the seeds from which all galaxies and cosmic structures eventually grew. ROSAT, the first great X-ray surveyor. A German-led mission with US and UK partners, ROSAT was launched in 1990 with a primary goal of performing the first ever all-sky survey with an imaging X-ray telescope. It created a massive catalog of over 100,000 X-ray sources, providing a foundational map of the high-energy sky that astronomers would use for decades. Hubble Space Telescope, the most famous scientific instrument ever built. Launched in 1990, Hubble is a versatile observatory that primarily sees invisible and ultraviolet light. By being positioned above the blurring effects of Earth's atmosphere, it has provided some of the sharpest and deepest visible light views of the universe ever captured. After a famous repair mission fixed its flawed mirror, Hubble went on to revolutionize nearly every field of astronomy, from discovering the accelerating expansion of the universe to imaging the atmospheres of distant exoplanets. It is both a scientific powerhouse and a global cultural icon. Compton Gamma Ray Observatory. One of the 4 great observatories, Compton's mission was to detect the most energetic and violent events in the universe. Launched in 1991, it mapped the entire sky in gamma rays. One of its most important results was showing that gamma-ray bursts are distributed nearly uniformly across the sky, strongly suggesting a distant cosmological origin and setting the stage for later missions to measure their distances. WMAP, the mission that took cosmology to the next level. Following up on COBE's discoveries, NASA's WMAP, launched in 2001, to measure the fluctuations in the cosmic microwave background with far greater precision. Its incredibly detailed map allowed scientists to nail down the age of the universe at about 13.7 billion years, determine its precise composition, including dark energy, dark matter, and normal matter, and confirm its overall geometry, ushering in the era of precision cosmology. Chandra X-ray Observatory. Another of the great observatories, Chandra is NASA's flagship X-ray telescope. Launched in 1999, its mission is to observe the universe in high-energy X-rays, which are emitted by extremely hot and energetic objects. With unparalleled resolution, Chandra studies the dynamics of exploding stars, the matter swirling around supermassive black holes, and the vast clouds of hot gas that permeate galaxy clusters. XMM-Newton, the European Space Agency's flagship X-ray observatory. Launched in 1999, it is a contemporary to NASA's Chandra. Its key difference is its larger mirror area, which makes it incredibly sensitive to faint X-ray sources. This makes it a powerful discovery machine, ideal for conducting large surveys and finding new black holes, neutron stars, and distant galaxy clusters. Spitzer Space Telescope. The final of the original great observatories, Spitzer was the infrared specialist. Launched in 2003, it could peer through clouds of cosmic dust that are opaque to visible light telescopes like Hubble. This allowed Spitzer to witness the birth of stars and planetary systems, study the composition of asteroids and comets, and analyze the atmospheres of exoplanets. It provided a crucial view of the cool, dusty, and hidden universe. GALEX. This NASA mission was designed to study the history of star formation in the universe by looking at it in ultraviolet light. Launched in 2003, GALEX conducted an all-sky survey, mapping the ultraviolet sky with tens of millions of detected sources, including millions of galaxies. Because UV light is a key tracer of young, hot, massive stars, the GALEX map allowed astronomers to understand how, when, and where stars have formed over cosmic history. Integral, the European Space Agency's primary gamma-ray observatory. Launched in 2002, Integral is designed to study the most energetic phenomena in the universe. It operates alongside missions like Fermi, but with a different specialty, using gamma-ray imaging and spectroscopy, along with complementary X-ray and optical monitoring to study violent events such as black hole accretion and supernova explosions. Neil Gehrels' Swift Observatory, a unique, multi-wavelength observatory designed to be a rapid response machine. Launched in 2004, Swift's mission is to hunt for gamma-ray bursts. When its wide-field gamma-ray instrument detects a burst, the spacecraft swiftly and autonomously reorients itself to point its powerful X-ray and ultraviolet/optical telescopes at the afterglow. This ability has revolutionized our understanding of these colossal explosions. Herschel Space Observatory. Before the James Webb, ESA's Herschel was the largest infrared telescope ever launched. Its mission was to study the far infrared and sub-millimeter universe, allowing it to see the coldest and dustiest objects. Herschel was a star formation machine, revealing the very earliest frigid stages of star birth hidden deep inside dense molecular clouds. Planck. This ESA mission was a dedicated cosmology machine. Its goal was to create the most detailed map ever of the cosmic microwave background, the faint residual afterglow of the Big Bang. The baby picture of the universe it produced allowed scientists to determine the age, composition, and geometry of the cosmos with unprecedented precision. WISE, the modern successor to IRAS. Launched in 2009, WISE performed a vastly more sensitive all-sky survey in infrared light. It discovered millions of new celestial objects, including ultra-luminous infrared galaxies, the coolest failed stars known as brown dwarfs, and, after being repurposed for a new mission called NEO-WISE, it became one of the world's most prolific hunters of near-Earth asteroids and comets. NuSTAR, NASA's high-energy X-ray specialist. NuSTAR is the first space telescope to focus light in the high-energy, or hard, X-ray spectrum. This allows it to study the most extreme and energetic objects in the universe with unprecedented clarity, including the physics of matter falling into supermassive black holes, the processes inside the remnants of exploded stars, and the true nature of collapsed stellar cores. Fermi Gamma-Ray Space Telescope, the powerful successor to the Compton Observatory. Fermi continuously scans the entire sky, studying the high-energy universe with much greater sensitivity. Its science program includes mapping the gamma-ray sky, studying active galaxies such as blazars, pulsars, and gamma-ray bursts, and searching for possible dark matter signals. Gaia. This is not a telescope for taking pretty pictures, but a revolutionary machine for creating the ultimate map. Gaia's mission is astrometry, to measure the precise positions, distances, and motions of over 1 billion stars in our Milky Way galaxy. The The data it is collecting is being used to build an incredibly precise 3D map of our galaxy, revealing its structure, history, and the way stars move within it. It is a galactic cartographer, providing the foundational data that is revolutionizing our understanding of the Milky Way. Kepler Space Telescope, the telescope that changed our place in the universe. Kepler's sole mission was to discover exoplanets using the transit method, by staring relentlessly at a single patch of sky and looking for the tiny periodic dips in starlight caused by a planet passing in front of its star. Its discoveries were staggering, revealing that planets are not rare, but are in fact more common than stars in our galaxy. Kepler single-handedly transformed exoplanets from a niche curiosity into a central field of astronomy. TESS. The successor to Kepler, TESS is a planet-hunting machine with a different strategy. Instead of staring deep at one spot, TESS is scanning the entire sky, looking for transiting exoplanets around the nearest and brightest stars. This makes its discoveries the ideal targets for follow-up observations by more powerful telescopes like the James Webb. TESS is building a comprehensive catalog of the most interesting planetary systems in our own cosmic neighborhood. NuSTAR, a unique observatory that is not a free-flying satellite, but an instrument mounted on the International Space Station. The neutron star interior composition explorer has one goal: to study the bizarre physics of neutron stars. By precisely timing the arrival of X-ray pulses from these ultra-dense, rapidly spinning stellar corpses, NuSTAR can determine their size and mass, providing crucial data on the nature of matter at the most extreme densities possible. SRG, a joint Russian-German high-energy astrophysics mission launched in 2019. Its primary instrument, ROSAT, is carrying out the most sensitive soft X-ray all-sky survey to date, with early catalogs containing roughly 900,000 X-ray sources, mostly active galaxies, plus thousands of galaxy clusters. Its goal is to use the distribution of these massive structures to create a new map of the large-scale structure of the universe. JWST, the scientific and spiritual successor to Hubble. JWST is the largest and most powerful space telescope ever built, a technological marvel designed to see the universe in infrared light. Its massive, gold-coated segmented mirror and giant sunshield allow it to peer back in time to see the very first stars and galaxies that formed after the Big Bang. It is also a revolutionary tool for studying the atmospheres of exoplanets, searching for the chemical fingerprints of potentially habitable worlds. IXPE. This NASA telescope has a unique and powerful capability. It can see the polarization of X-rays. While other telescopes measure the brightness and energy of light, IXPE measures the orientation of its waves. This provides a new window into the universe, allowing scientists to directly map the geometry and strength of the extreme magnetic fields around objects like black holes and neutron stars for the first time. XRISM, a joint JAXA/NASA mission. XRISM is a powerful X-ray spectrometer. Its mission is not just to take pictures, but to break down X-ray light into its component colors or energies with incredible precision. This allows scientists to measure the temperature, composition, and motion of the superheated gas found in galaxy clusters and flowing away from black holes, providing a new understanding of the chemical evolution and dynamics of the universe. Euclid, the European Space Agency's dark universe detective. Launched in 2023, Euclid's mission is to tackle the two biggest mysteries in cosmology, dark matter and dark energy. It will create a vast 3D map of the universe by observing billions of galaxies out to a distance of 10 billion light-years. By measuring their shapes and distribution, Euclid will track how the universe's structure has evolved, revealing the influence of these invisible cosmic components. Nancy Grace Roman Space Telescope, the next great NASA observatory. Roman is a wide-field infrared telescope with a field of view 100 times larger than Hubble's. It is designed to tackle the biggest mysteries in cosmology, including the nature of dark energy and dark matter, by mapping the structure of the universe on a vast scale. It will also conduct massive surveys to find thousands of new exoplanets using the gravitational microlensing technique. SDO. While most space telescopes look out, SDO looks at our own star. It is NASA's next-generation solar observatory, taking high-resolution images of the Sun in multiple wavelengths about every 12 seconds. This provides a continuous, stunningly detailed view of the Sun's dynamic atmosphere, allowing scientists to study the mechanics of solar flares, coronal mass ejections, and the solar dynamo that drives our star's activity. Thanks for watching. Which space telescope do you think has had the biggest impact on astronomy? Let me know your thoughts in the comments. Also, please remember to like and subscribe if you enjoyed this video.